In this video, we're going to talk about the limit of a function. Our objectives here are going to be to find limits from a graph and understand limits conceptually, to introduce the concept of one-sided limits, to identify when a limit does not exist, to estimate limits from a table, and to estimate limits using the graph and sketch graphs of functions given information about limits. So let's just recall from last time. In general, we write limit as x approaches c of g of x is equal to L, and that's how we would read that. So our preliminary definition, for limits of a function, suppose that a function f is defined for all x near a, except possibly at a, if f of x is arbitrarily close to L, as close to L as we like, for all x sufficiently close but not equal to a, then we write the limit as x approaches a of f of x is equal to L. This definition here is something that we don't get into specifically in this class formally, but if you want to look at this in your book, this is called a delta epsilon proof, where epsilon is the error in L, that we have L plus or minus epsilon, and we have x plus or minus delta, that we get this little interval maps into that little interval, and that's a more formal definition. So if you hear anyone talk about a delta epsilon proof, they may do that at other schools, especially if you're going to be a math major. You may want to take a look at that. That'll be an important concept later, but we don't make that a primary objective of this course. Your teacher may decide to go over that, but we won't go over any of that today. All right, so informally, the limit as x approaches a of f of x equals L if f of x gets closer and closer to the value y equals L, as x gets closer and closer to the value x equals a. It's not always true that the limit as x approaches a of f of x is equal to f of a. In fact, there are many instances where this isn't true, and they are more interesting. For example, this graph right here, if we have a as 2, f of a is right here, is the solid dot, but as I get close to a from the left and from the right, the limit is actually going to be 3, but f of 2 is equal to 5, and they're not equal to each other. But let's look here at 1. As I get close to 1 from the left and the right, it equals the function value of 2. And at 3, right here, we can see that as I get close from the left and the right, I get closer and closer to 4, but the function actually does not exist at x equals 3. So this is undefined, but we're getting closer and closer to 4 for our limit. So we can have a limit exist and a function value not exist. We can have a function value exist and the limit exist. We can have a function value with no limit if there's just a single point there and I don't have any activity from the left and the right. So finding limits from a table. So create a table of values of f of x equals the square root of x minus 1 over x minus 1, corresponding to values of x near x equals 1, and then make a conjecture about the limit of f of x as x approaches 1. So as we stick in values like 0.9, 0.99, 0.999, and so on from the left that are a little bit less than 1, and values like 1.1, 1.01, 1.001, 1.0001, we can see as we squeeze in from the left and the right, it looks like we're squeezing in on 0.5 is what that appears to be. And so let's evaluate this limit as x approaches 1 of the square root of x minus 1 over x minus 1. We can't use direct substitution. If we try that, we get 1 minus 1 over 1 minus 1 is 0 over 0, which is undefined. We actually call this an indeterminate form. Indeterminate form. More on that later. But we're going to use some factoring, or we're going to use our table method, or we're going to rationalize the numerator. Something like that. We'll do some algebra when we see an indeterminate form. So our conjecture right now from the table, since we're not doing anything algebraically, is that the limit as x approaches 1 of the square root of x minus 1 over x minus 1 is equal to 1/2. So for some functions, analyzing function behavior around a point will be necessary. So let's go ahead and keep going here with the definition of a one-sided limit. So right now we're going to talk about right-sided limits, where we're coming from the positive side of the x-axis. So suppose f is defined for all x near a with x greater than a. If f of x is arbitrarily close to L for all x sufficiently close to a with x greater than a, we write the limit as x approaches a from the right of f of x is equal to L, like that, and say the limit as x approaches a from the right. I just said that. Equals L. For left-sided limits, suppose f is defined for all x near a with x less than a. If f of x is arbitrarily close to L for all x sufficiently close to a with x less than a, write limit as x approaches a from the left of f of x equals L. And for the limit to exist, the limit from the left has to equal the limit from the right. So let's estimate limits graphically and numerically. Let f of x be equal to x cubed minus 8 over 4 times x minus 2. And let's use tables and graphs to make a conjecture about the value of the limit of f of x as x approaches 2 from the right, and the limit of f of x as x approaches 2 from the left, and the limit of f of x as x approaches 2 if they exist. So we have this graph here. I'm going to zoom in a little bit for you so that you can see it more clearly here. And that's a little bit more zoomed in than I wanted. There we go. That's about how zoomed in I want to be here. All right, so x cubed minus 8 over 4 times x minus 2. The computer generated graph is inaccurate because we're actually undefined at x equals 2. So there's actually a hole in the graph there because we can't divide by 0. So we need to manually put that hole in there. We can't see it because it's only a single pixel in the graph, but make sure that you account for the domain here, that x can't be equal to 2. So now as we get close to 2 from the left and the right, it sure looks like we're getting close to a value of 3. That's what it looks like to me. And let's go ahead and let's see if we can establish that with our table. So here's our table of values. So as we get close to 2 from the left and the right, and we see that we go 2.8525, 2.985025, 2.998500025, 2.999850000, so on. We're getting closer and closer to what looks like 3 here from the left and also from the right. 3.1525, then 3.015025, then 3.00150025, and 3.00150000. Looks like I'm closing in on 3 there. So let's go ahead and make that conjecture here. Graphically, it appears limit as x approaches 2 from the right of f of x equals 3, and limit as x approaches 2 from the left of f of x is also equal to 3. And it also looks like limit as x approaches 2 from the right of f of x is equal to 3 here. From the right is from this side here, coming this way. Looks like I'm squeezing in on 3 from this side. And this is limit as x approaches 2 from the left. And that also appears to be approaching the value of 3 as I come from the left. And since these values are equal, then limit of f of x as x approaches 2 is going to be equal to 3, only because the limit from the left and the limit from the right are the same. So this requires left and right limits are equal. When we say that the limit exists, that's what we mean, that it has the same limit from the left and from the right. So relationship between one-sided limits and two-sided limits, assume f is defined for all x near a, except possibly at x equals a. Then the limit as x approaches a of f of x equals L, if and only if limit as x approaches a from the right of f of x equals L, and limit as x approaches a from the left of f of x equals L. So a function with a jump discontinuity. We haven't really talked about what continuity is, but if the graph jumps and has two disconnected pieces, usually piecewise defined functions, but sometimes they'll have these absolute value pieces in them like this. We want to sketch the graph of g of x equals 2x squared minus 6x plus 4 divided by the absolute value of x minus 1, and use the graph to find the values as limit of g of x as x approaches 1 from the left, limit of g of x as x approaches 1 from the right, and limit of g of x as x approaches 1 if they exist. So let's go ahead and think about the absolute value of x. And it is in two pieces here. This is y equals negative x, and this is y equals x. So it can be written as x for x greater than or equal to 0 and negative x when x is less than 0. So let's think about this here in that way. So g of x on the interval of x greater than 1 is going to make this positive down here. Will be g of x is, and that'll just be plain old x minus 1, 2x squared minus 6x plus 4 is equal to 2 times x squared minus 3x plus 2 over x minus 1 is 2 times x minus 1 times x minus 2 over x minus 1, and that will cancel there, and we'll have the limit equal to 2 times x minus 2. And for g of x on the interval x less than 1, g of x is going to be equal to 2x squared minus 6x plus 4 over a negative x minus 1. So similar but different, x squared minus 3x plus 2 over a negative x minus 1 is going to be negative 2 times x minus 1 over x minus 2. X minus 1, I just brought that negative up there. It's going to be negative 2 times x minus 2. So that gives us 2 times x minus 2 when x is greater than 1, and negative 2 times x minus 2 when x is less than 1. But we don't have a value when x equals to 1 because we'll get 0 over 0. So that's going to look like this. Here, if we stick in x is 0, we get negative 2 times negative 2 is a positive 4. If we stick in 1 into this piece for the limit, 1 minus 2 is a negative 1. Negative 2 times negative 1 is a positive 2, but there's an open circle there. And those 2 points determine this line. If we stick 1 into this piece up here, 2 times negative 1 is negative 2 with an open circle. Stick in 2, 2 minus 2 is 0. So we have an x-intercept there, and those 2 points determine a line. There's arrows on the ends of both of these, but we see that the function is undefined there at x is equal to 1. So this is g of x for x less than 1, and this is g of x for x greater than 1. That's going to be g of x equals negative 2 times x minus 2, and the limit of g of x as x approaches 1 from the left is going to be -2 times -1, sorry, times 1 minus 2 is -2 times -1 is a +2. And the limit as x approaches 1 from the right of g of x is going to be this stuff from the right here. It's 2 times 1 minus 2, 2 times -1 is a -2. So because the limit from the left and the limit from the right are different, because limit as of g of x as x approaches 1 from the left does not equal limit of g of x as x approaches 1 from the right, limit as x approaches 1 of g of x does not exist. We don't call it undefined. We say that the limit does not exist. So function values are undefined, like this open circle right here, but this limit does not exist. That's what we say there. All right, we have some strange behavior that happens sometimes, like oscillations, and things will start oscillating really quickly and we can't see what's happening on the graph. We try and use our table method sometimes to help us analyze and discuss the limits shown here in this image. This is actually the image of cosine of 1 over x. And we want to look at what happens as x approaches 0. And so limit as x approaches 0 of cosine of 1 over x. This, as we see, it's going down and up and down and up, and it's oscillating, and it's oscillating very quickly, but it's not approaching any single pattern there. So that does not exist because there's no pattern for oscillating functions like this. There will be some other functions that we'll specifically talk about later that have special limits. Even though they oscillate, that we'll be able to tell you exactly what their limit is, and you need to memorize those special limits. So graph the following function and find the values. F of x is equal to 2x minus 4 for x less than or equal to -2, and x squared if x is greater than -2. So first let's find f of -2. So we look for which part it's equal to, stick -2 in here. 2 times -2 minus 4 is -4 minus 4 is a -8. Then we're going to find the limit as x approaches -2 from the right. So that's going to be this piece. That's going to be -2 squared is going to be a +4. -2 from the left. We already did that. That's this piece that has the less than. So that's 2 times -2 minus 4 is -4 minus 4 is a -8. So we have from the left and from the right are not equal. So this limit does not exist. Because from the left, we get towards -8, and from the right, we get towards +4. So remember, if the limit from the right does not equal the limit from the left, then the limit of the function as x approaches that a value does not exist. All right, that's it for this video. And we'll come back next time and we will talk more about limits. Let's see here. We come back, we'll talk about techniques for computing limits. So we'll see you for the next video.